So I'll write down what is the, at least I outlined the steps to calculate 1 over T1 based on first principles. That it's either you take the,
Hello. Will you be attending the class today, NMR class? So are you coming, sir? It's just now he has come. Oh, okay, come. Yeah. He's coming, he forgot.
Okay. So, if you remember, it's there in the previous lecture anyway, we calculated it, at least I outlined the steps of calculating 1 over T1. One is through this Fermi-Golden rule, where you have this, fluctuating fields are basically, you want relaxation of the nuclear system. So in compensation, the electron system, so that's the lattice.
Sorry, sir.
No, we also came just now. I was talking to them in the lab. I just realized we are late already.
ऊपर ही थे क्या? Actually इधर एक conference.
I was saying that's what the conference. It starts now or afternoon?
No, tomorrow.
Oh, tomorrow actually. Okay. I was wondering 25th and 26th.
Yeah, 26 to.
So that's one way. Other was the Redfield way, where there's a density matrix approach to write d rho by dt based on some commutator, minus I h bar commutator of the Hamiltonian with rho, and so on. So I just outlined the steps. The result is what I'll write. I'll just summarize. So whether one way or the other, finally you get different ways of writing this. So I call this A here. So we are looking at nuclear spin lattice relaxation. That 1 over T1 is gamma square by 2. This gamma is the nuclear gyromagnetic ratio. And then you have an integral over time dt e to the I omega naught t. And then you have these expectation value of the fluctuating fields. The transverse ones are the ones which cause relaxation. Okay. This omega naught is just the precession frequency of the nucleus, whatever applied field, DC applied field. And this is also written as the integral. Is also written as some j of omega naught, also called the spectral function. Spectral function of the electron fluctuations. Then there is another way to write this. So there's the Moria way. So you basically write, so these are the fluctuating fields. So you write H plus in terms of S plus, the spin, electron spin operator. So you can write A by gamma H bar, then it's correct in our units. Otherwise, it's basically proportional to the spin. You have electron spin, which is fluctuating. Through a hyperfine coupling A, it is that dynamics is causing something at the nuclear side. So this H plus can be written in terms of S plus and H minus in terms of S minus via hyperfine coupling. The precise units will determine whether you write the A as A, then it's in field units, or A as A by gamma H bar, then it's in Ørsted per mu B. Those are details. But basic point is that Moria wrote this in another way, where you write this in terms of the spin operators, and then with the explicitly the hyperfine coupling present. Okay, right now it is just the fields. So once you do that, it looks as follows. So this is the form B, and so 1 over T1 is again nuclear gamma square, and you have this integral, same thing, dt e to the I omega naught t, and the H plus H minus, I will evaluate rather it written in terms of via the hyperfine coupling S plus S minus, and then further writing in terms of the Q dependence. Okay, so you have another change there, and then so you have a summation over Q, and then so dependent, and then A square. So it's just the hyperfine coupling. I have written there's a different way of writing it, and then the Q dependent part, again transforming from real space to reciprocal space. Okay, and then you have instead of the H plus H minus, now you'll have S plus S minus. Okay, so generically in Moria's one, he writes it like this. So you have a Q and T dependent. So S alpha QT, S alpha. Let's write again so that I don't go beyond that. S alpha QT, S alpha minus Q0. Okay, and then this is also just like the other one you wrote in terms of this spectral function. This is written as gamma n square by n. So what is n? You are basically summing over various Q values in the first Brillouin zone. So what are the values, various values? So that will be n, right? I mean, how do you remember how you get that? Quantization, I mean, even in a non-quantum mechanical approach, because you'll have periodic boundary conditions, so that basically brings in, so 2 pi by n, and then integral multiple of 2 pi by n. So even when you solve the phonon problem, you have that, right? So that's where that comes in. And so you have a sum over first Brillouin zone for all Q values. There are n such for an atom, and then so therefore there's a 1 by n. So this final expression looks like, compact way it is written like. Okay, so all those, other than the AQ square, all those other things are captured in this S of Q of omega. This goes by the name of a dynamical structure factor. So both the forms, the form in terms of H plus H minus, which is that integral of the spectral function, or Moria's way of transforming in terms of Q dependence and writing it in this form, where again it's gamma square times something involving this integral of spin operators. So it's called the dynamical structure factor. So in an inelastic neutron scattering experiment, you will actually measure this S at specific Q values, because you can set up your experiment where some energy, neutrons are incident with some energy wave vector, and you're detecting at different energy, different wave vector. So you can, Q specific thing you can obtain. Right, then so it's not left at this point, it's further reduced to the following. So this is a dynamical structure factor, then using fluctuation dissipation theorem, and we always have, almost always have, our relevant energy scale, the precession frequency, the energy corresponding to that is essentially always much less than the thermal energy. And so then this 1 over T1, so this I call equation C, this looks like 2 gamma n square kBT by n sigma over Q AQ square chi double prime Q of omega naught. right? So it's the same thing. The dynamical structure factor in this limit using fluctuation dissipation theorem now has been written in terms of the dynamical susceptibility. So you write it in general chi as chi prime plus I chi double prime. So it is that dissipative part, chi double prime.
N square?
It depends on the units. So
Last day
I will, yeah. So out here, so this chi double prime, you are looking at relaxation of one nucleus because of whatever are around it. So this chi double prime is actually the atomic susceptibility. Okay, because this one via hyperfine coupling is interacting with whatever is electron moment here. So what is the atomic susceptibility is what is there in the summation. But in practice we always write you write always molar susceptibility. So then if you write a molar one, then you have to divide by another n, and then Avogadro number, etc. I'll write it in that form also. And in this form, A has the units of field. Okay. To get it in our Ørsted per mu, you have to divide by a gamma h bar. But this is the form you'll find in Moria's paper. Yesterday we were looking at that, 1956 or 1962 or 63 paper. So this is the form you will find. This is another form then that was solved in case the kind we use. So then the form D, so with change of units, form C, I converted to form D, which we use in practice. That's the reason I'm writing it that way. 1 over T1 equals 2 gamma square kBT by Avogadro number squared, and sum over Q of, so I write this separately as AHF just to distinguish it from the A that I wrote earlier. This is in slightly different units, that's all. A square, and then chi double prime Q of omega by omega. And here the AHF in units is in units of Ørsted per mu b, and chi double prime is in units of centimeter per. So again, as a side note, our usual cases, this also has a so-called form factor of the hyperfine coupling. There may not be sort of very significant Q dependence, and then you don't need it inside the summation. You can just take it out and just use the value, and the summation chi double prime can be separately done in the limit of small omega, whatever it is. There are special cases where this actually plays a very central role. So I just quickly give the example of high TC cuprates. So what was the situation was, you had copper here, copper 2 plus, oxygen 2 minus, copper 2 plus, and this was a 180 degree bond. In the high TC cuprates, you had these copper in the chain and copper in the plane, so you had a square planar CuO network, and the CuO was 180 degree. Okay, and of course undoped one, it is antiferromagnetic long range orbital. The atrium is somewhere here. Okay, actually not like this. What you have is, I think you have these square planar copper, and then I think atrium is somewhere here center. So this is copper, and atrium is over here. So this was a fantastic compound in many ways from NMR point of view, because in good situations you could do copper 63 or copper 65 NMR. You could do this is spin 3/2, so it would be sensitive to local environment, quadrupolar term in the Hamiltonian. So you could do pure NQR. So lots of interesting things. Structural change you would be able to detect. This one is spin half, so some different advantage here. That lines are narrow. You don't have to worry about this the quadrupole part. Now oxygen has two isotopes: oxygen 16 and oxygen 17. The naturally occurring one is of course 16, what we breathe. Oxygen 16 has no nuclear movement, so there's no scope of doing NMR with oxygen 16. However, oxygen 17, I don't remember now offhand, but it's been 3.5, I think. But point is, oxygen 17, you don't have even, so you deviate from that. Now this has a nuclear moment. And so you can do another. Problem is that it's naturally occurring oxygen at almost 0% of oxygen 17. These high TC cuprates, whether it is, there are different varieties.
5/2.
5/2. So you could very easily put in and remove oxygen in here. So oxygen 17 you can buy in a cylinder, tiny, not like our helium big cylinder, but tiny one. It's very expensive. And then in your preparation process, you first maybe prepare as usual, then pull out the oxygen in some reducing atmosphere, then connect it, I'm saying it loosely, connect the helium oxygen 17 cylinder to your furnace, and then reoxygenate with oxygen 17, and then you will get in some maybe 1% or something oxygen 17, still in spite of all that, and then you can do measurements on that. So this was fantastic in the sense you could do copper, you could do yttrium, you could do oxygen, and each gave some different kind of information. So specifically, so the fluctuations between the copper are antiferro in this, and the finally ordered state is antiferro. So the form factor, because of this antiferro fluctuations, actually makes makes it cancel at this oxygen site. So antiferro fluctuations, when you measure oxygen 1/T1, so you can do measurement of 1/T1 of oxygen, copper, yttrium, etc. as a function of temperature. It just showed, I'm just saying nominally, some behavior like this. So because the word that it uses, the antiferro fluctuations are filtered at the oxygen site. It's located symmetrically between the 180-degree bond, and it's located symmetrically between the antiferro fluctuating copper. And so because of the form factor AQ, you can calculate that. That gets cancelled out 1/T1 because of, so A is dependent on Q, chi is dependent on Q. There is a dominant chi from the antiferro part at Q equal to pi by A. But because of the A getting 0 at Q equal to pi by, that gets filtered out. So the antiferro fluctuations you don't sense when you measure oxygen 17. On the other hand, if you measure at the yttrium, then one calculates the form factor, it doesn't get filtered out. So one sees something like this. So there are cases where this plays a prominent role, the hyperfine Q dependence of the hyperfine coupling. But right now, even in this BaFe2AS2, this iron arsenide superconductors, there also different nuclei were used to probe local dynamics, and there also it doesn't cancel out, but there also the form factor plays a role. Okay, it's not 0 exactly, but it's not, you cannot just get it out of the integral saying that it's Q independent. Okay, so there are some Q dependence which play a role. So general form is this: A square chi double prime Q of omega. Very often we just pull this out and just work out the rest. But there are special cases where the form factor plays a role. High TC being one, not so recent anymore, 30 years back, 40 years back, but yeah, that was one prominent situation where it played a role. So going back to that form, so now, okay, we'll consider sort of various cases. So let's say you have just like the high TC, for example, you are looking at atrium being relaxed by local moments of copper, antiferro connected copper, right? So if you have exchange coupled moments and you are at sufficiently high temperatures, okay, so basically in the paramagnetic regime, but you have these antiferro coupled moments. So we can assume a Gaussian approximation of the correlation function. So again, you can look at it in statistics, for example. If you have random fluctuations, then in the limit of a large data set, it always goes to a normal distribution. Okay. By the way, I don't know, some of you might have. There is a Canadian guy who started a thing called Veritasium. He has a lot of interesting things in maths, physics, etc. So he has an episode on. So you have these normal distribution, Gaussian. You have some which have a log normal distribution. So x-axis, it's not actually symmetric. It's squeezed on the low side and it tapers off with a large tail. But you plot x on the log scale, then it looks symmetric. So that's called a log normal. Then you have a power law. We encounter power laws in many situations. So both log you put and then you have a power law. So different physical situations which then follow these behaviors. So power laws are apparently so prominent in so many things. So he has an episode on these different power laws, log normal, etc. It's very interesting. He has on many other things also, by the way. You have seen some of them, yeah. So you have seen also, yeah.
He prepared liquid nitrogen and helium from some small bottle. He did a lot of
that I don't know. Yeah, a lot of different physics experiments also. So anyway, what I wanted to say was that in the limit of large data in certain situations, you always get a normal distribution. You're asking, why Gaussian? There's some central limit theorem which tells that large data set will go to a normal distribution. So if you assume, we'll have another situation also. If you assume s plus t, s minus 0, two-third s into s plus 1 f of t. Okay, we are looking at only transverse fluctuations. So imagine average value of s square is s into s plus 1. So for each component is one-third s into s plus 1. We are considering only two transverse components, so two-third s. Roughly that's the reason for the two-third s into s plus 1, and then you have a time dependence. So there is a f of t, and if you take f of t as e to the minus omega ex square t square by 2, Gaussian form, then what is 1 over t1? That, remember there's a form, this is part of the integral that e to the I omega naught t, and then so minus infinity to infinity. So this integral is easily worked out. It's some error function, right? E to the x square minus infinity to infinity. So one works out, and then what one gets. So another technical sort of term is that. So any function you can define first moment, second moment, third moment, and so on. So all you have to do is integral of second moment means integral of x square f of x. Third moment is x cube f of x, and they correspond to line width and things like that. Okay, so second moment of f of t, this Gaussian form, works out to 1 over omega x. Okay, if you do just calculate, it works out to 1 over omega x. So, I had a doubt for a bit that, Gaussian, why should I take it as minus omega square t square by 2? Why not just minus omega square t square? Gaussian form. So, that's okay, nothing wrong with that, but then, we are finally connecting this with some line width in our problem. So, this is the standard form, with this, the second moment is 1 over omega exchange, that's the exchange frequency. You have fluctuating antiferro moment, so that's the relevant omega ex. So, if you do this, then 1 over T1, you do in the S plus S minus, you do the integral, then 1 over T1. So, imagine you have a nucleus and you have Z prime local moment neighbors. So, each of them is contributing, uncorrelated, each of them is contributing to the relaxation. You just have to add effect of each of them, right? So, that Z prime is the number of near neighbor local moments to the nucleus, which are causing the relaxation. Then you have a gamma square, A square, maybe AHF, sure. And then you get a root, this comes from the Gaussian integral, by the way, root 2 pi S into S plus 1.
In T1 sir, that's why we use under root of 2 pi. Yesterday I was searching that for normal we
Yeah.
use 2 pi.
Yeah.
That constant. It's,
Yeah.
proportionality constant.
Huh.
But for T1 we use under root of 2 pi. This 2/3 of it's transverse component.
Because of transverse component, and the 2 pi, root 2 pi and all comes out because of the e to the minus x square integration.
Okay, here.
E to the minus a square x square is the root pi, error function, no? Root pi by a. So that root pi comes from there actually.
Oh, okay.
So this is the final form where again the omega ex has to be defined. So this is j ex by h bar root 2/3 z times s plus 1.
Sir, S into S plus 1 I think ऊपर नहीं रहेगा.
No, it's there both places.
This will be Z prime.
This one is z because you have, so each local moment has with this fluctuations with z other local moments,
The nearest neighbors.
nearest neighbors. So that's why that figures in a mean field thing. So this is z.
And that Z prime.
This is the nucleus interacting with z prime nearest neighbors. So nuclear local moment and this local moment. If you don't, I know this is coming suddenly, what's all this, because you're not even familiar with the equation, right? But you can ask, we can try to make it simple maybe.
So like, again repeat whatever I do.
Yeah, so what is the situation, physical situation? So you have a nucleus here. Okay? And then it has, so there's some orbitals, and then you have electron moments located, at different nearest neighbors. Okay? How many are there? So some Z prime. Okay? So this is fluctuating, it is causing relaxation. This is fluctuating, it is causing relaxation, and so on. So I'm just adding the effect of, they're uncorrelated fluctuations. We are in the high temperature limit. So each is causing, so each gives that 1 over T1 as, without the Z prime, this thing. And so for each of them the same, so it is Z prime multiplied by that. In addition, what's happening with the local moments? Now each local moment means electron moment. So each local moment has how many other local moments as neighbors? Okay.
So this is just nearest neighbor which
Nearest neighbor. So those are Z in the neighbor.
In our system, there is magnetic atom, right?
This is the magnetic atom. Yeah. These are the magnetic atoms. So each has how many? It has Z neighbors. So when you are calculating the Curie-wise susceptibility, the theta involves effect of all the neighbors. Okay, so that's why there is a, in the denominator, there's that Z that appears. And of course, this is for a situation where you take the Hamiltonian as J SI dot Sj. Nearest neighbor, and not 2j but j, plus or minus sign. That's not the point, but yeah, j si dot h. Okay, so often this is the final form that we use. So if you want to calculate what is the T1 among these due to these moments in the high temperature limit, okay, where they are just uncorrelated fluctuation, then this is the thing. So in practice, what do you do? From a bulk susceptibility measurement, and you know what atom you are looking at, copper or cobalt or whatever, you know what is S. Okay, spin half or 3 half or whatever. So this is known. You have done a detailed NMR experiment, so you have plotted K in terms of the susceptibility, so you know the hyperfine coupling from calculation. And this exchange frequency of these fluctuating local moments can also be determined because you know, through some route you have this information, because bulk susceptibility behaves in a Curie-Weiss-like manner. Right? You have so chi is C by some T minus theta. Huh? And then the theta in a mean field approach, you can write theta in terms of Z, S plus 1, J, etc. Okay. So by bulk susceptibility measurement, by the way, C actually involves N G square mu B square S times S plus 1 by 3 AB, you know, something like that. Okay. So from a measurement of the bulk susceptibility with temperature, from the slope, for example, and additional information, you know the S, you know the theta, and so one can estimate exchange frequency. Usually something like 10 power 14 hertz, 10 power 15 hertz, very high. Okay. So from the experiment, everything is actually known. So one can, this Z, Z prime are also known from the structure. So one can estimate what should be the 1 over T1 in the high temperature limit. And then you can check, you know, does it follow that? And it should deviate from this constant behavior as you come down in temperature, because this is uncorrelated moments. When correlations start building in, then you should get a deviation from here, right? Which you do see in so many cases. Okay. Then some other, this is often useful. So Monica, you're asking other than there should be some temperature. Where's the temperature gone? Temperature has gone away because you had a KBT in the numerator, and then like a Curie susceptibility, so 1 over T from the susceptibility. That's why you have the S into S plus 1, N G square mu B square S into S plus 1 by T. So that T has cancelled. That's why the T is gone from the problem. High temperature anyway, it's temperature independent.
सर रेयर अर्थ वगैरह में ये फॉलो करेगा ये पैटर्न पैरामैग्नेटिक है तो it doesn't
This is
matter.
a general, yeah.
It should not matter.
This is a general formula.
I think it should work for errors also. This is a localized mode.
Localized, in fact, yeah, localized. This for localized moments. Now you have, since you bring in localized moments, they have slight variations. So long ago, people have looked at, you know, ppm of iron or ppm of manganese in copper. Copper is metal. You just dope in very small amounts of impurities, so single impurity model. So there's a lot of interesting physics there. And of course, this can be measured in NMR. You can look at copper NMR in the absence of impurities, or if you put in controlled number of impurities, you know. So what do you have? What do you have over there? You have the nucleus. Okay, nuclear moment, and I mean this is a matrix of conduction electrons, right? And then you have this iron or manganese or whatever local moment. So so we are considering a case where the chi double prime is from dilute local moment. So you are just, I mean the simplest is single impurity. So single moment, and then you're looking at effect on relaxation. So this is now mediated through conduction electrons. Okay. In this situation, so again our limit is always omega going to 0. NMR frequencies are very small, megahertz, compared to the other energy scale in the problem. So in this limit, sigma chi double prime q of omega by omega is equal to Avogadro number, the local moment susceptibility, which is temperature dependent, times tau by 2 pi, where tau is the electron or local moment relaxation time. So here again, so this is, so your 1 over T1 involves other factors, but this part, the sigma chi double prime, can be written like this, and the chi local can again, maybe from experiments one can estimate, because pure copper has some temperature dependent susceptibility. You add in 1 ppm of iron, you start getting a Curie term, so you can measure that, so you might be knowing the local moment susceptibility. And so this may be a way to estimate tau, which is then related to well, many fundamental things, but yeah, right. Yeah, sure. So this is one useful form where you have a situation of nucleus, and earlier we were considering essentially all localized picture. Here it is not localized picture, but you have a nucleus, and then you have these conduction electrons. So you have a sea of conduction electrons, and in the conduction electron sea lies some local moment. Okay, so the hyperfine coupling is through the conduction electron, not really through orbitals, like nearest neighbor, nothing like that. So this may be far away, but through conduction electrons are everywhere. So through that sea of conduction electrons, it conveys the fluctuations. So in that case, the 1 over T1 you can rewrite by writing the summation as some chi local times tau by 2 pi, where this tau is the local moment relaxation time. Okay, so the form that you get in this, so once you put back, you get 1 over T1. So this is my form E. What you get 1 over T1 is 2 gamma square kBT by Na. AHF square, assuming Q independent, chi local, which is a function of temperature in general, tau by 2 pi. Just putting the summation ka part back into the expression for 1 over T1, this is what you get. So of course, if you are looking at a shift because of the local moment, so that's the also K. So in this case, and there's a temperature here, so in this case you will get 1 over K T1T equal to constant. So usual Fermi liquid case was K square T1T. So that's quite different, of course this is different, but here you'll get a K T1T. So in practice it's been examined in these kind of systems. Then, so we looked at what? Gaussian variation for the spin autocorrelation. You can also have an exponential variation of the spin autocorrelation. And yet another form, so I'll just show others also. So if now S plus T, S minus 0 is like e to the minus t by tau c. Not earlier we said some s square times e to the minus omega ex square t square by 2. So Gaussian, not Gaussian now, let's say exponential. Okay, where tau c is this correlation time, then one can obtain the spectral function. It looks like h square 2 tau c by 1 plus omega square tau c square. You can easily do the integral, like a Lorentzian. Okay. and one can then obtain the 1 over T1, right? Just gamma square by 2 times the spectral function. So you get 1 over T1 is, so gamma square is there, by 2, that 2 goes, and then you have a h square tau c by 1 plus omega square tau c square. So this is also called, I mentioned before also maybe, red field formula. So yeah.
So like how do we know which correlation we have to, like earlier you were saying we have Gaussian, now we have exponential, so like how one knows?
Yeah. So one has to look the physical situation in the problem, and yeah, there's yet one more variety also I'll tell you. Yeah. So a priori one may not know. So depending on actual physical situation, one has to guess what kind of correlations are there.
This is also at high temperature.
Very well, as long as you have the exponential. Yeah. So yeah, you're saying.
So can we also maybe fit our experimental data and then check?
Then yeah, we're back on this. Yeah, then it says that it has. Yeah.
A bit of tedious task.
Yeah. So this is also seen in many situations. So in fact, this mu-SR experiment one does, where you implant muons inside. So muons are spin polarized when they are produced in the accelerator. So they implant like this, and you can do the experiment and then they respond to dynamics of local moments inside your sample, and then they depolarize. So that depolarization rate is called lambda, which is basically like 1 over T1. Same thing, transverse fluctuations of the internal field will cause depolarization of the, it's not the nuclear moment, it's the muon moment. Okay, so mu-SR lambda, the standard variable that it's called lambda, is same as 1 over T1 actually. It's the relaxation rate for the muon polarization. Here is the relaxation rate of the nuclear polarization. Okay, so you can do this experiment in different longitudinal fields, for example. Okay, so you can change the omega in the problem. Omega is gamma h. You can change the omega in the problem and then look at 1 over T1. So which in mu-SR is called lambda. How the lambda depends on the applied field, longitudinal field. And then from that estimate tau c, and then based on that get some insight. So this is also commonly used in mu-SR, longitudinal field experiment, where you vary the applied field, and then as of at various applied fields you measure them. So some of you who have done mu-SR, the muon polarization as a function of time, so looks sort of like this. So this depolarization comes from nuclear moments also in that case. You have muon inside and you have nuclear moments which are fluctuating. That can cause depolarization. Plus you have these electron moments which may then freeze or alter or whatever, they also cause. So usually at high temperatures, such a form, this Gaussian-like form is observed. So this is muon depolarization, so mu-SR. So muon depolarization. So it's 100% polarized to start, and then with time it depolarizes. So at high temperatures, when the depolarization is only due to nuclear moments, if you have nuclear moments. For example, if you're looking at copper sample, then there'll be copper 63, copper 65 nuclei. Those have magnetic moments, they are fluctuating. They'll cause depolarization of the muon. Okay, so one can fit this to, there is a, again by two Japanese physicists by name Kubo and Toyabe, there is a Kubo-Toyabe form, which is at low times it's Gaussian and then it falls in some manner. Okay, it has some structure also, how it tapers off. So there's a Gaussian Kubo-Toyabe. You can fit it to this and obtain the lambda. Okay, how this is decaying. Now, as you come to lower temperatures, you will have these electron moments now playing a dominant role. Okay, so often one does this measurement as a function of temperature. So this is at T1, some different temperatures. So as you come down in temperature, often so this is from nuclei. This depolarization is from nuclei. Once the electrons start dominating the depolarization, it's often exponential. Okay. So once it goes to electron, the shape also then it goes like this. So you get a change of lambda with temperature, and so this is the case here, and here maybe due to electron movements.
Like depending on the magnitude of the movements or just presence.
Again, spectral function and how they are coupled to, again, like a hyperfine coupling. Here also there's something like that. Usually dipolar in this case, but yeah, so it depends on some parameters. But usually at low temperature, then this will dominate, where you have significant local moment fluctuations. And so so these are the two kinds of experiment one does. So this is in zero applied fields, usually called the ZF experiment. So it's a really true ground state. You didn't apply any magnetic field, unlike the NMR experiment, you have to apply a field. And then you monitor what is the lambda as a function of temperature. And then if there's an ordering transition, for example, you will see a divergence. So some structure to it depending on how the dynamical susceptibility is changing with temperature. Okay. So this is one experiment one does, where you will track what the shape of the depolarization is at different temperatures in zero applied field, magnetic field. The other experiment one does is that you sit at one temperature and then change the applied field, longitudinal field. Okay? And then that also changes lambda because of this, because you are now changing omega. Okay? So you have a muon inside, and you are changing the longitudinal field, so it's like the DC field of the NMR. Okay, so basically one gets 1 over T1 as a function of the field. So from this one extract lambda with H and all, and then obtain some insight. Okay, so these are the usually two kinds of experiment one does. So lambda in zero field, and then in a field with variable field. Okay, so very often where you have ultimately some glassy transition, so you have this exponentially decaying autocorrelation. We work often on this QSLs, right? Quantum spin liquids. So there, in some of them, so exponentially decaying autocorrelation means the spin value at time equal to 0, and at a later time how that is correlated with the initial, right? That's what it is telling. So it's dying out very fast, right? Exponentially decaying with some characteristic tau C correlation. In these quantum spin liquids, there are some extended correlations present. So the form is not quite exponential. People have derived this form. There's a power law part to it. So this rather goes as S plus S minus and T to the minus X, E to the minus T by X. Okay. So one Gaussian form, which we did, that leads to some kind of 1 over T1. An exponential form, again that's seen in so many cases, that leads to this Lorentzian type 1 over 1 plus x square variation. And then in the recent times, a power law, so in the integral you have to do this, and then where this x is some exponent which you figure out from the experiment really. For what value of x does the data fit well? Okay.
Does it become something like the gamma function, like the integral t to the power minus x e to the plus like this gamma function?
If you had, for gamma function you need integer values, something like that. Yeah. I don't think you can solve in closed form the integral.
Yeah, maybe only for integers.
So main point is that it's not just exponential. At long times there is some correlations present.
Mhm.
Okay, so quantum spin liquid, so they're strongly entangled, strongly correlated. So that's reflected in something like this. And so the lambda in this case with h, earlier case it was this Lorentzian type of form, 1 over 1 plus x square type of form. In this case, it works out to some, so this is the Kubo-Toyabe width from the nuclear moments, 2 delta square, some tau to the x, integral 0 to infinity, e to the minus x, e to the minus mu t, and just the cosine gamma h e. So you have all these different forms possible. So Sushant was a student, so we measured on, there's a triangular copper moment system where you had the funny structure, but you have, so if you're aware, I might write it down. This is, you might think like it's a 1, 1, 3 and 3 unit cells. Okay, so you might think of it like a triple perovskite. Okay, ABO3, so A3, B3O9, and then the B3 is mixed with Cu and Sb. So he could make it where there was a Cu Sb site ordering. So Cu Sb Sb Cu Sb Sb and so on. We could see superlattice peaks in the XRD. Okay, from this superlattice ordering. So if you look at that structure now and you look at the 1-1-1 planes, it has only copper in a triangular fashion. So it was a cubic-like structure, and so sorry, the other side. Actually, it's on left color.
Sir, I need to add a meeting actually.
Go ahead. Yeah. Right, so this is nominally the cubic structure, and different color matter. Color is not changing. Anyway, so the 1-1-1 plane has triangular arrangement of copper. Okay, and these are, so you have Cu, then Sb, Sb, Cu, and so on. So basic point is that you have copper planes which are triangular, and so that provides the source of frustration. And we found this is all characteristics of a quantum spin liquid. And the μSR that we measured here, lambda followed this kind of thing with some exponent which are similar to other QSs. So yeah, there's a whole variety. Gaussian correlations, exponential correlations, exponential times some kind of power law correlations. So what that f of t is, it depends on the physics of the problem. Do you know a priori what it is? Not always. Yeah, then let's start on this and then we can sign. Color change is not working. Right? Oh, I understand. So it should be on pen. Yeah. Yeah, the other thing we'll do is just start and then maybe complete next time. So, for spin equal to half, we worked out what the relaxation rate is. So, detailed balance. So, you have two levels. Population is increasing because of nuclei, transiting from. So, you have some plus half and minus half. So the rate of change of population of this level is because something increases because of something coming in from here with some rate, and decreases because something leaving from here with some rate, right? W plus minus and then and so on. So you just write dn by dt, right? Rate of change of the population as a combination of with the plus sign what is increasing, with the minus sign what is decreasing. You solve that, you get the simple exponential variation of the magnetization is the difference between, right? So if this is N1 is an N2 or the population, then magnetization is proportional to nuclear magnetic proportional to N1 minus N2. So once you write the dn by dt and solve those, then you write N1 minus N2, that works out to have an exponential variation with time, with whatever initial condition. Right? So this we worked out. We want to do the same now for spin 3. Okay, so in principle it's the same thing. Now you have 4 levels. So you have m equal 3 half, half, minus half, minus 3 half. Right? 3 half lowest, then half, then minus half, minus 3 half. So let corresponding populations be n1, n2, n3. Okay. Now
So what we are trying to ऐसे समझ गए कुछ heading के लिए what is the final thing?
you want to find out what the relaxation law is for spin 3 half moments. Spin half we worked out. No. What is you want to find out what is dmz dt. This came out to be m0 minus mz by d1. Now, of course, those are 2w. 1 over d1 was 2w. We said w plus minus approximately w minus plus, and so ultimately you get a 2w. So this was the, so therefore you get the fitting function that you measure. This works for spin 3 spin half. Non-spin half, we have to work out. No, this is not obvious. Now you have different levels. So that's what we are trying to do. What is the law relaxation equation for example, spin 3 half? Okay. Now point is, let's say, okay, 3 half to half, we call it W12, the transition probability. Okay. Half to minus half, one way or the other, we call it W23, right? And then minus half to minus 3 half, minus half to minus 3 half, W34. Okay, these are the rates. Now, how are we usually writing the rate equations? You have to write dn by dt as some w times something, for minus w times something, and so on, right? Here it's the same 2 levels. So you have either w plus minus or w minus plus. Okay, which in that limit we said equal. Now it's not so simple. If you are looking at this level, okay, there is some transition. So increase because of something coming from here, increase because of something coming from here, and decrease likewise from the other way. So you have involvement of this one, W23, but also W12. Are these equal?
No.
So I can sort of guess that W12 and W34 will be equal. What determines transition rate? Fermi-Golden rule? Square of the matrix element. What is the matrix element you are trying to do? What is the selection rule? Magnetic fluctuation.
Delta
Plus minus.
So only those are allowed.
हाँ.
So that means your matrix element is of what? I plus or I minus, right?
हाँ.
You would have a matrix element like
M plus and M minus 1.
something like that, or I minus with
Yes,
this
yes,
thing.
yes.
So this will depend on what the M is.
हाँ. बिल्कुल.
You know what it is, right? So because I plus minus acting on M gives you root I times I plus 1 minus M times M plus 1 M plus minus 1. Maybe you valid only for plus. Minus. So, I is fixed, but you know, if this is 3/2 or half, that's going to change. So, the W12, W23, they're not going to be the same. Okay, but you can work out, na? So, and then you have to do, you'll get some square root of, so 3/2 times 3/2 plus 1. And then depending on what M you are looking at, so if you are looking at 3/2 times 3/2 plus 1, and let's say you are looking at this is minus half, and then this will be plus half, right? So then you can put accordingly value of M and all that. So if you work that out, in one case you'll get square root of 3, in one case you'll get square root of 4, and so on. So W12 will be, you know, the ratios. W12, if it's 3W, then W23, the central line has more weight, is 4W, and W34 is again 3W. This you can easily work out. Agreed?
Yes.
Because when you're doing W12, then you're going from
3 by 2 to 1 by 2.
so accordingly you put those numbers and see what you get. When you're doing this one, you're going plus half to minus half. Okay, so accordingly you can put that. And so, unlike the spin half case where you know there are only two terms in dn by dt and same w, here it's different now. So with this now you can write down. I'll just write this and the details we'll do next time. So n1 dot, you know, any question? Shall I move that?
What is W?
Transition probability.
For what?
So going from half to minus half now. So
okay, half to minus half, that is we call it W.
I mean, they're in the ratio 3:4:3. That part is clear, and then other parts in the matrix element which are not dependent on this will give something. No? So that is at W. Right? So it's your transition, your Fermi-Goldner rule is transition probability, W is some 2 pi by h bar square of the matrix element. We just found out the square of the matrix element. Other prefactors will give something. Those are the same. So that is some W. Okay, only the numerical factor that we worked out. So for example then, n1 dot is turns out minus 3W, n1 minus n2. If you are looking at the last level, lowest level, then there is only transition with only one because delta m is plus minus 1. So you have a decrease because of something moving out and an increase because something coming from 2 to 1. So, and then the rates are the same, so it works out like this. Similarly, n2 dot equals 3W n1 minus n2 minus 4W n2 minus n3. Right? When you're, remember what the levels are? You have 1, 2, 3, 4. This is actually half minus half. Sorry.
3 by 2.
3
Minus
half,
3.
half minus half
Minus 3.
Okay. So when you are looking at this level n2, then there are transitions from 3 and transitions from 1. That's why you get n1 minus n2, but also n2 minus n3. You know, both transitions are there. Similarly, you will write n3 dot equals 4w n2 minus n3 minus 3w n3 minus n4. And finally, n4 dot is of course symmetrically with this 3w n3 minus n4. So earlier with the 2-level system, we had a very simple situation. We now with 4-level, because the rates are there's only a W. And now, depending on the level, this one, this transition rate, half to minus half has more weight, 4, while the other has 3. Right? So they have different weights, which is reflected here. So, what are we trying to work out? Magnetization is proportional to what? So we are going to look at a case, for example, in which you irradiate only the central line. Okay. So initial situation is what? Some Boltzmann distribution of populations. You apply a pi/2 pulse. Let's say if satellites are out, you irradiate only the central line. So you apply a pi/2 pulse. After that, what's going to happen? These populations are equal now. You destroyed the magnetization, only for central line though. So these two populations are equal. Others no change, same as before. We didn't touch them. We didn't touch, no. We said pi/2 pulse will hit only the central line. So this is our initial condition. We have to solve these equations, no. So simple linear, dn by dt is something times n. Easy to solve, more variable, but detail we'll do next time. So we need to know initial conditions. Initial condition is that these are now difference is 0. What is it actually? We'll write down. And these are just the equilibrium values. For n1 and n4, it's just equilibrium values. n2 and n3 are equal. And how much? We'll write down. Not so difficult to write down. So the problem is now to be able to solve this, because ultimately, what is the nuclear magnetization? It's n2 minus n3. Start with 0 and finally it is going to some equilibrium value, which also we know. Which way is it going? That we need to find out. It's not going to be a simple exponential because you are going to get transitions from here and as well as from here, and with different weights and all compared to the central one. So a little bit tricky. So we'll write in a compact form and we'll work out. So the traditional way is to write the deviations from equilibrium. Okay, that's xi, which is ni minus ni0. There's the equilibrium population, and then at some time t, it is some population ni. How much is the deviation from that equilibrium? That we call xi. Okay, and then equations are written rather in terms of xi, so you'll get basically x dot as some matrix times x. Right? We had 4 equations, so you'll have x1, x2, x3, x4, and then you have a 4x4 matrix, so this is just a compact form for writing those 4 linear equations. Okay, so I'm just telling you what the process is. After this, you have some matrix A, which we can easily write down. We have that here. We just have to group them properly, and we'll know what the elements are. Okay. So we need to, in mathematical language, we need to now diagonalize this A. It is not purely diagonal. Okay, so you have to find eigenvalues, eigenvectors. Okay, and then solve it to see dx by dt is x means exponential variation. Okay, but exponential variation with how many eigenvalues are there? Other one that has only one eigenvalue, 2w, well 0 and 2w, 2 eigenvalues were there. Now it will have 4 eigenvalues. So you can have a combination of 4x, e to the minus 2w, e to the 0t, 2wt, 12wt, and 6wt, and each with a different prefactor. So this is what we have to do. We have to figure out the eigenvalues of this matrix, then find out the eigenvectors, and with the initial condition given, we have to see how it evolves with time. Okay, this is the sort of brute force hard way of doing it. Then there's a way I learned using Klebs-Gordon coefficient where you can write in a compact form, and then those are maybe tabulated somewhere. You use those, and then we are done. Okay, so I'll stop with this. What we want to do is basically find out eigenvalues and eigenvectors. Our initial situation is, you are 1 and 4, you are at equilibrium. So in terms of x, you are no deviation from equilibrium, right? This is 0 for n1 and 4. This one is some delta and minus delta, right? Because one you depleted and the other you added, so that you have a net zero magnetization basically. So this is the initial situation for x1, x2, x3, x4. So we have to solve this by writing, you have to now write this in terms of the eigenvectors. You figure out the 4 eigenvectors. This needs to be written down in terms of some C1, eigenvector 1, C2, eigenvector 2, C3, C4. And then the time evolution is just e to the, corresponding to each eigenvector, what is the eigenvalue? You'll have basically e to the 0t plus, some coefficient e to the minus 2wt plus some coefficient e to the minus 6wt plus some coefficient e to the minus 12wt. So depending on how you decompose this, some will contribute, some will not. It turns out because of some symmetry, only the 2w and 6w, only those contribute for the spin. So this detail will show next time. Okay, so you can imagine if you do brute force, spin 5 halves, you will get how many levels? 6 levels. 6 levels, not 2i plus 1.
Yes.
So 6 by 6 matrix. So you have to diagonalize a 6 by 6 matrix. I mean, nowadays you just throw it into ChatGPT or some computation, it will tell you what the eigenvalues, eigenvectors are. But this is the process. So, spin 7 half, again 8 by 8 matrix. But you don't need to do all that. So these values, there is a, again I'm telling you in advance, so the various eigenvalues are with a minus sign are just this k times k plus 1, where k is 0 to 2i. So k runs from, in unit steps, 0 to 2i. So for spin 3 half, it runs from 0 to 3, 0, 1, 2, 3. And the various eigenvalues are 0, 2w, 2 times 2 plus 1, 6w, 3 times 3 plus 1, 12w. Take spin 5 half, the next one you can write down this. So we'll see this later. So this is known. The eigenvectors is not so simple, but I mean, point is, ultimately you are solving this simple equation. You just have to diagonalize this A. Okay? And so this various forms of relaxation work out very easily. So you have to provide what the initial conditions are, of course. Then the time evolution is known. Okay, so next time I'll do this, the residual part of this. You will also work out some of it. And then we go to what the quadrupolar Hamiltonian is. So you do a basically multipole expansion of the charge distribution of the nucleus, and then how that couples with the electric field that is present. Field, its gradients, next derivative, and so on. And so that change in Hamiltonian, how does that translate into change in the line shape? Various other practical things. Okay, stop here.